Welcome back. In this video, we'll look at section 1.2.3. We'll start talking about constructions on subspaces. Again, we're trying to find more examples and being able to put examples that we already have together and construct new ones. That's going to be helpful. All right, so let's define this right away. Definition 1.2.3. I'm going to start with two subset, X and Y. So I'm not saying subspace because the definition will work even with general sets of a set Z. The intersection of X and Y is the subset of Z which contain all elements that are in both X and Y. So here it's going to be the set of all Z and Z, so that Z is in X and Z is in Y. So here in the following diagram, if I take all of the elements of X and draw them in yellow, I'll get this. Now if I do the same thing for the elements of Y, I'll get this. The elements of the intersection are things that are in both red and yellow sets. So everything that's slightly orange here, let me draw it even deeper in orange, this would be X intersection Y. So they're elements that belong to both sets, X and Y. All right, now next, the union of X and Y is the subset of Z which contain all elements that are either in X or in Y or in both. All right, so this is Z which is in X or Z is in Y. I don't need both, but I could have both, that's fine too. So in the second drawing here, if I'm drawing in yellow X and I'm drawing in red Y, then X union Y is everything I've colored. So let me use a completely different color because otherwise it's going to be a mess. But here, everything that is colored either in red, in yellow, or in orange, that would be the union. And then if on top of this, X and Y are part of a vector space, so if Z is a vector space, then we have the operations that are defined, and I have a sum X defined. So the sum of X and Y contains all the elements of Z that can be built by adding one element of X with an element of Y. All right, so this is the set of, let's write it this way, X, well, actually let me use A plus B, so that A is in A and B is in Y. All right, so we can't really sketch this without having some information about the subspace and what the operations are, because it does depend on the sum at least. All right, so here's the question that we want to answer. If X and Y are actual subspaces of the vector space Z, all right, so they're closed under addition, they're closed under scalar multiplication, and they contain the zero element. So the three properties are true. Which one or which ones of X intersection Y, X union Y, and X plus Y are going to be subspaces of Z? All right, so what I'll do in the next video, I'll look at one example in R3, and then we'll actually quote the theorem. All right, so I'll see you then.